Here we're looking at multiple view drawings. The orthographic views are created through a theory, okay, a procedure where we enclose the object with a glass box that has sides that are perfectly perpendicular to one another. So you have a top, front, and a right side to the box, and a picture is generated on the glass box with lines of sight that are perpendicular to the not to the object, but to the glass box side, okay, to the plane. So we position a normal type surface object, of course, parallel to these is our initial task. So in the front view, there's no way to show the difference in depth. We can only show height, which you see indicated by this little H, and width. In the side view, we can show depth of those surfaces, so we can see where this surface is located in the right side view, where it is actually right here, represented by this edge. Then the next surface that's adjacent to it is a little deeper. And then the next surface is yet deeper. We also see the shape from the top. Here we see depth and width. So each view shares a dimension with an adjacent view. So side view and top view share depth. Front view and top view share width. And side view and front view share the height. The projection planes of the box, as I said, are perpendicular to each other. Okay, these regular planes are shown here, and in the computer systems we use these planes for creating 2D or 3D drawings, representations or models of objects. It's called our coordinate system, X, Y, and Z. So here we'd have a plane looking into the front that would be a Z direction this way, and this way would be an X direction, and this way the depth would become the Y direction. So the horizontal plane that we see up here is called the XY plane. This is called the XZ, and then this one would be the ZY plane. So each line of sight is perpendicular to each projection plane. Okay. Looking perpendicular allows us to have a true projection, a true size view of our object. So looking at the description in the book, surface 1, 2, 3, 4 is parallel to the front projection. So 1, 2, 3, 4. Going in a clockwise direction, we've numbered the points of the plane. When we look from the top, 1, 2, 3, 4 appears as an edge of surface A, B. Okay, so we would actually have point 1 and 4 and 2 and 3. 1 and 4 being underneath A and 2 and 3 being underneath B. Here we see it in the pictorial. In the side view, 1, 2, 3, 4 appears as an edge of surface, and we're calling it CD. Behind C, point C is points 1 and 2. And behind D is point 3 and 4. This occurs in a normal plane or a normal surface view of an object. So reading orthographic views involves integrating this type of information about every surface on the object. Right? So reading these and then drawing these, you draw them a plane at a time, or you analyze a plane at a time, determining if it's normal, inclined, or oblique surface, and you do it one surface at a time. I tell students all the time, working with orthographic projection, solving an object orthographically is like eating an elephant one bite at a time. So take heed of that and look at an object one surface at a time and determine where that surface is in the front, what it's lined up with and located with in the top, which then you have solved all three dimensions of height, width, and depth. The third view, the right side view, confirms it and would be used to show profile or shape that the top view and the front view may not be able to show, and so forth. Sometimes you don't need three views for a drawing, let's say, of a washer, a disc with a hole in it, or a rectangular plate with some holes drilled in it. You wouldn't need a side view, may not even need a top view, but two views and sometimes just one view will tell all the information we need to know about the object. So that is your job as a drafter, is to determine how many views do I need to fully discuss or fully show this object in true size and true shape. All right, next we're going to be looking at our 6 regular orthographic views.